Swayam Prabha. Digital India. Educated India.
Hello everyone, this is the last lecture of module 2. I hope you have thoroughly enjoyed the module 2. And in the lecture today, we are going to cover the concepts such as precritical waves and also the critical waves. And we are going to also talk about a very special type of wave, that is a evanescent wave. And then we will move on to do the reflection and transmission coefficient for the evanescent wave. Before we even go and talk about all these waves, we are going to have the recap of the previous lecture. So in the previous lecture, we talked about Snell's law. When the wave is going from one medium to another medium, then the horizontal ray parameter of the ray remains constant. That means the sin theta by V1 is equal to constant. And then we have talked about the takeoff angle. And this is the angle at which ray leaves from the source. It is also measured in the plane containing source and receiver. And then we went on to derive the reflection and the transmission coefficient using the two boundary conditions for the SH wave. The boundary conditions were the displacement is continuous across the boundary of two medium, and also the attraction should be equal across the boundary of both of the medium. So the reflection coefficient that we derived was having the expression this one, and the transmission coefficient that we derived was having the expression this one. And then we discussed about Fermat's principle, in which it was stated that the ray path between 2 points are those for which the travel time is extremum. It can either be minimum or it can be the maximum travel time. Then let's start with the evanescent wave. This is basically also known as the inhomogeneous wave or the head wave, and sometimes it is also referred to as the post-critical waves. So it generally evolves at an angle, at an incident angle greater than the critical angle, and when the incident angle is greater than the critical angle, the transmitted wave is trapped just below the interface. That means, let's suppose there is this medium, this is the interface of two medium, and this is the normal at this interface, and the ray is basically incidenting at an angle Ji, that is greater than the critical angle. Then the energy, there will be energy that will be reflected back, and there will be energy that will be transmitted and will be trapped just below the interface. That means just below the interface, maybe it may be having the amplitude that will be decaying with depth, and you can see like it should be something like this. And this wave is known as inhomogeneous or the head wave or the post-critical wave, and also it is known as the evanescent wave. So let's suppose the incident angle is Ji and the critical angle is Jc. Then we can write the reflection and transmission coefficient for the pre-critical waves. So what are pre-critical waves? Pre-critical waves are the rays when the incident angle is lesser than the critical angle. So if that is happen, then it will follow the normal Snell's law. And we have seen it in the previous class that the reflection and the transmission coefficient was having expression something like this. We have derived this expression in the previous class for the SH wave. So the reflection coefficient we got was rho1 beta 1. Beta 1 is the velocity in the medium above the interface, and the beta 2 is the velocity of the medium below the interface, and rho 1 is the density of the medium 1, and rho 2 is the density of medium 2, and J1 is the incident angle and J2 is the refraction angle. So J2 is basically this angle here. This should be J2. So the reflection coefficient for the pre-critical rays is rho 1 beta 1 cos j1 minus rho 2 beta 2 cos j2 divided by rho 1 beta 1 cos j1 plus rho 2 beta 2 cos j2. Similarly, the transmission coefficient for the SH wave is 2 rho 1 beta 1 cos j2 divided by rho 1 beta 1 cos j1 plus rho 2 beta 2 cos j2. So similarly, we can also talk about the rays where the incident angle is equal to the critical angle. So you know the critical angle is the angle at which the refraction angle will be 90 degree. So that means these rays will be known as critical rays, and these will be perfectly refracted ray. Perfectly refracted ray means the refraction angle is 90 degree. In that case, the reflection coefficient will be equal to 1 and the transmission coefficient is 2. So this is the geometry of the critical rays. So you can see like the incident wave is having the incident angle that is equal to the critical angle, and there will be the reflected energy, and there will be the energy transmitted and will be traveling at the interface, parallel to the interface, and that is basically having the angle 90 degree. So if you want to apply Snell's law in this case, what you will see is that sine of ji divided by velocity of the upper medium is beta 1 is equal to sine of jc divided by sine of this should be the reflection angle. So sine of j2 divided by beta 2. So as I said, the incident angle is equal to the critical angle. That means this will ji will become jc, sine of jc by beta 1. That will be equal to sine of j2. j2 is 90 degree. So that sine j2 will become 1. So 1 by beta 2. So in that case, jc will be equal to sine inverse beta 1 by beta 2. That is how you can find the critical angle between two medium. Now let's talk about the post-critical waves that are also known as inhomogeneous waves, or also known as head wave or the post-critical wave. So what are the names? Inhomogeneous waves, inhomogeneous waves, and also head wave, and also the post-critical wave, and is also known as the evanescent wave. Okay, so now in that case, the incident angle will be larger than the critical angle. So that is what it is written here. So when the reflection will happen, when the incident angle is larger than the critical angle, the reflection angle, the reflected wave will be phase shifted, and the transmitted wave will be an evanescent wave that decays exponentially with depth. So this is the reflection coefficient for the reflected wave, and this is what the transmitted wave will be having the amplitude decay in this form. So you can see the reflected wave, the reflection coefficient will be e to the power 2 iota theta. Iota is the imaginary term, and theta, the value of theta will be tan inverse mu2 r2 star divided by mu1 r1. We are going to talk about r2 star in the lateral slides. So this is the geometry which basically describe about the post-critical rays. So you can see there is this incident wave which is coming at an angle larger than the critical angle, and there will be the reflected energy which will be phase shifted, and there will be these evanescent wave, and you can see the evanescent wave is having the decay with depth. So, and also like you can see with the expression, it is exponentially decaying, and which will be having the decay in terms of something like this, minus k2 in the bracket 1 minus cx square by beta 2 square. So cx is the horizontal apparent velocity, k2 is the wave number in the second medium, and beta 2 is the shear wave velocity in the second medium. So let's recall some of the formulas that we discussed about in the previous lectures. So this arc beta, we define this parameter as equal to the ratio of the vertical wave number to the horizontal wave number, that is kz by kx, and p is the horizontal parameter. So basically it is 1 by cx, that is sine ji by beta, is equal to kx by omega, and neta is the horizontal, neta is the vertical vertical slowness, that is 1 by Cx, that is cos ji by beta, is equal to kz by omega. Now, as per the Snell's law, the apparent horizontal velocity is Cx, across the interface should be equal. So that means P is equal to 1 by Cx, that will be equal to sin J1 by beta 1, that will be equal to sin J2 by beta 2. So this is basically nothing but the Snell's law, which says that the apparent horizontal velocity across the interface should be equal. So now, let's talk about when the incident angle, that means J1. So what is J1 and J2? So that's about, this is the interface and there is this normal, and the energy is incidenting at an angle J1 and it is refracting at an angle J2. So we are talking about J1, that is the incident angle, and JC is the critical angle. So when J1 is greater than JC, then you can write sin J1 greater than sin JC. You are just taking a sine of both of the sides. So what will basically happen? Sin J1 is greater than beta 1 by beta 2, because sin JC is beta 1 by beta 2, because as I told you in the previous slide, that if the energy is having the refraction angle 90 degree, that is the case of when the incident angle is equal to the critical angle, then that means sine of JC by beta 1 will be equal to sine of 90 degree by beta 2, and sine of JC will be equal to beta 1 by beta 2. So that is what it is written here. So sine J1 is greater than beta 1 by beta 2. So then after you do little bit of rearrangement, then what you will get, beta 2 is greater than beta 1 by sine of J1. And this is nothing but beta 1 by sine of J1 is the horizontal apparent velocity, that is Cx. So this means that when J1, that means the incident angle in the first medium, is greater than the critical angle, then beta 2 is greater than Cx, which means that the velocity of the second medium will be greater than the apparent horizontal velocity. So now let's see the displacement of the transmitted shear wave from the previous lecture. So this is the displacement of the SH wave. You can see that when the SH wave is traveling, or you can say that when the SH wave is traveling in XZ plane, then it will be having its vibration into the Y direction. So that is what it is written. So Uy of the transmitted wave, this is for the transmitted wave. So Uy transmitted as a function of x, y, z, that will be equal to b dash, that is the amplitude in the second medium of the SH wave or the transmitted wave, e to the power iota in bracket omega t minus horizontal wave number kx x minus horizontal wave number kx r2 z. So now this, what is r2? R2 is nothing but kz by kx. So when you will replace it here, so this entire thing will become kz. But we are writing kz in terms of r2 and kx. Now let's recall that neta beta is equal to under root of 1 by beta square minus p square. So this neta beta is nothing but it is the vertical slowness. So as we know, as we have seen already, neta square plus p square is equal to 1 by beta square. So when you will rearrange it, you will get this particular expression, and r beta, that is that will be equal to kz vertical wave number divided by horizontal wave number. Then you can basically see that neta is what? Neta is the kz by omega that we have seen in the previous lecture, and that will be equal to, when you will multiply the numerator and the denominator to kx, then what you will get? This expression you will get, and this is nothing but this is your small p, that is horizontal slowness, that is p, and this thing is nothing but this is your r beta. So basically you can write this p also, you can write 1 by cx. So this thing will become r beta by cx. So that means your neta, this neta is equal to r beta by cx. Now if you will incorporate this into this equation 1, then what you will get? R2 by cx is equal to under root 1 by beta square minus p square, and then we know that p is equal to 1 by cx, then you can get R2 as equal to under root of Cx square by beta 2 square minus 1. So you can basically understand here that if Cx is greater than 1, that means this will be a real quantity. In case if Cx is less than beta 2, that we have seen in this case, particular case, where the incident angle is greater than Jc, then what will happen? The beta 2 will always be greater than Cx. That means Cx will be smaller than beta 2. So what will happen in that case? If Cx is smaller than beta 2, then this overall quantity will goes to less than 1. In that case, the under root will be having a negative term. That means R2 will be a imaginary quantity. Now, that is what it is written. R2 will be an imaginary quantity if Cx is less than beta 2. So, if Cx is less than beta 2, then we can take minus 1 outside of the under root. Then R2 will become plus minus iota in bracket under root 1 minus Cx square by beta 2 square. So let's focus on the z component of this displacement. So the z component of this displacement is what? The iota kx R2 is the z component. We want to see how the wave as transmitted SH wave behaves with depth. So for seeing so, you need to consider this particular term and see how it behaves. Now, if you look at this term, let's focus on z component of the transmitted SH wave. So that is iota kx R2. Okay. Now, since R2 we have seen it is having this expression. So we have incorporated that in place of R2 here. So that will be here. And that will be iota kx. If iota we will take that this iota and this iota will multiply and that will be minus 1. And finally you will get plus minus kx in bracket in under root 1 minus Cx square by beta 2 square. If you will look at this quantity, this is basically a real quantity, right? If this is a real quantity, then if you look at this expression, this is a real quantity here. So this real quantity, what you will see that the wave, either you can consider plus or either you can consider minus. If suppose you are considering plus, then what will happen? The wave will basically grow exponentially away from the interface. If it is growing exponentially away from the interface, then in that case the conservation of energy, the law of conservation of the energy will not hold true. So in that case, the plus term you cannot consider. Now you left with the negative term, and which will basically hold true for the wave trapped at the interface. So that is what it is. So we are left with a wave that decays and it is trapped at the interface. Now, if you rewrite the displacement of the SH wave, then this is the displacement of the SH wave. Okay, so u t y x comma z comma t. I am sorry, this should be actually t here. U x comma y comma t. And when you will rewrite it, then what you will get? You will get b dash e to the power iota omega t kx minus kx r2z. And then if you will just decompose all the exponentials, then what you will see b dash e to the power iota omega t e to the power minus iota kx x and e to the power minus iota kx r2z. And now if you look at this particular term here, this one, then e to the power minus iota kx r2z will be what? It will be this thing. This we have just seen, right? So you are just replacing kx r2 here with the quantity that we just saw it here. Okay, so when you will replace it, then you will get this, and this gives rise to the evanescent, inhomogeneous or the head wave, which is basically similar to the PN wave. So PN wave is basically nothing but it is the wave that travels along the interface of the crust and the mantle boundary. And that crust and the mantle boundary is known as discontinuity and by the name MOHO. Okay, so the MOHO is the discontinuity which separates the low velocity crust from the high velocity mantle. So along that particular boundary, there is a wave that travels that is known as PN wave, and this PN wave is nothing but it is similar to the evanescent or the inhomogeneous or the head wave. So basically now after doing all this, we can define a new exponential term here. So the new exponential term here is R2 star, and that is basically iota in bracket 1 minus cx square by beta square under root. And this R2 star, we can say that it is equal to minus iota R2 because we defined the R2 here. This R2 is this thing, and we are considering R2 star as plus iota 1 minus cx square by beta square to the power under root. Now this R2 star, we can say it is minus iota R2, or equivalently we can say R beta 2, because beta 2 is the velocity in the second medium, R beta 2 star, that is iota R beta 2 for the reflected wave. The reflection coefficient rather being this. So if you remember, in the case of SH wave, we have seen when the incident angle was lesser than the critical angle, the reflection coefficient was coming like this. So this R beta 1 can be replaced with R beta 2 star. Sorry, R beta 2 can be replaced with this R beta 2 can be replaced with R beta 2 star. So R post, that means the reflection for the post critical waves, reflection coefficient will be having this expression, right? So we can write this, basically this quantity in the polar form, and in the polar form it will be something like this: R post is equal to e to the power iota 2 theta. If you compare with this quantity R e to the power iota theta, that is the polar form of the imaginary number, the R is basically 1 here. So that means the magnitude is 1. And the shift of the phase is 2 theta, and where theta is this quantity. So the phase shift is 2 theta here. Okay. So this phase shift depends upon the angle of incidence, since R is equal to kz by kx. That is the ratio of vertical wave number to the horizontal wave number, and this kz varies with angle of incidence. So what we have seen for the reflected ray, the magnitude is 1, and the reflected wave phase will be shifted by 2 theta, that where the theta will be tan inverse mu2 R2 star by mu1 R1, and the transmitted ray that will be trapped will be decaying with depth as an exponential term of this, that is kx in bracket 1 minus cx square by beta 2 square to the power under root. So in the summarized form, what we have learned today. So what we have learned, for the pre-critical waves, where the incident angle is less than the critical angle, the reflection and the transmission coefficient will be as derived in the previous lecture we have seen. For perfectly refracted wave, where the incident angle is equal to the critical angle, then the reflection coefficient will be 1 and the transmission coefficient will be 2. For the post-critical waves or the evanescent waves, where the incident angle is larger than the critical angle, the transmitted wave will be trapped just below the interface, and the reflection coefficient will be 1 with a phase shift, and wave will be phase shifted. The reflected wave will be phase shifted after reflection, and the transmitted wave will be an evanescent wave that decays exponentially with depth. So this is the expression by which the evanescent wave will be decaying exponentially with depth. So this is all for module 2, and these are the references. In the next module, we are going to talk about the surface wave and its dispersion, where we are also be deriving the expression for the displacements for the Rayleigh wave and the Love wave, and we will also see what are group velocities, what are the phase velocities, and other things. So that is all for the module 2, and with this we are ending this module. Thank you so much. Bye bye.